one more thing.
Yeah.
Okay.
So let me first see if just a moment. This thing, present this. Okay. Second, share screen, and this one share. Is this visible?
Yes, that's visible.
Okay, and then stop. Okay, and then I'd like to see if the video is shareable or not. Oh wait, I have to share sound, right?
Yeah.
Share. Okay, just this thing, QuickTime Player, share the sound, share, and what's this? Okay, what's this? Zoom can detect my microphone. What's this? Am I audible?
You are audible.
Okay. Why am I unable to share sound? Okay. Parameter tuning. Is this audible? The key observation is that of these approaches,
Yes, that's
there
audible.
are very few. Okay, awesome. So that's fine. Okay, cool. Then I think let's just wait for 2 more minutes and then we can begin the session.
Mm-hmm.
Okay, cool. That's nice. Stop share for now. Okay.
Great.
Okay, I think we're ready.
Mm-hmm.
Just get my headphones. Okay, I think we're ready to begin. It's time. Okay, welcome everybody. This is session 4 of research paper track, and my name is Raj Dabre from NICT Japan, and I'll be chairing this session. Before we get started with any of the presentations, I'd like to first share, just a moment. Yeah, I'd like to share the list of sponsors, being Google, Pangenic, Microsoft, and Apple. And in this session, there are going to be 4 papers. The list of the papers is available over here. We have R10 to R14. R10 is investigating softmax tempering for training neural machine translation models. R11 is scramble train translation problem of denoising UNMT. R12 is make the blind translator see the world, a novel transfer learning solution for multimodal machine translation. R13 is sentiment preservation in review translation using curriculum-based reinforcement framework. And R14 is on nature and causes of observed MT errors. Okay, with that done, I'll start the first presentation. And the first presentation is investigating softmax tempering for training neural machine translation models. And actually, I am one of the co-authors of this paper. So Kevin will be handling the chairing for this particular paper, and then I'll take over for the others. So I'll play this talk. Just a moment.
Hello, I'm Raj Dabre from NICT Japan, and along with my co-author Atsushi Fujita, I'm happy to present our work titled Investigating Softmax Tempering for Training Neural Machine Translation Models. Our work focuses on addressing some core issues in neural machine translation. One main problem in neural machine translation is overfitting, which is a big issue in low resource settings. The main reason being that overfitting reduces the generalizability capability of a model and therefore prevents it from reaching the best possible translation quality. The current solutions for NMT overfitting are by leveraging data, parameter regularization, and hyperparameter tuning. The key observation is that of these approaches, there are very few softmax-centric regularization methods. I mean, there are methods such as label smoothing and entropy maximization, but apart from these, there are not many well-known approaches. We believe that the softmax is an important part of the model because that is where the observable action occurs. By observable action, we mean the generation of the tokens. Therefore, we propose a new training method where we perform softmax smoothing prior to computation of loss using temperature, which therefore makes the softmax harder to overfit. The result is that we have an approach called as softmax tempered training, and we observe that it leads to improvements in BLEU, especially for low resource situations. Let me give you a background of the transformer NMT model, which we used in our paper. The transformer model is an attention-based encoder-decoder model where the encoder and decoder consist of stacks of layers. The way the transformer model or any neural machine translation model is trained is by minimizing the softmax cross entropy loss, where the probability of predicting the ith word is computed by the softmax of the logits for that particular word. The loss is computed by the negative of the log of the probability and the label of the word that should be produced. Now remember that this label is by default smooth. The issue is that there is no explicit regularization on softmax that is performed, and this is what we want to address. So our approach, softmax tempering, involves first dividing the logits by a temperature coefficient indicated by T, where T is greater than 1. Of course, you have to multiply the loss by T for gradient rescaling, and you can read our paper for a better explanation. Note that softmax tempering itself isn't very new, and it has been used for knowledge distillation. But to the best of our knowledge, no one has used it directly for training neural machine translation models. As you can see on the figure on the right-hand side, this softmax tempered prediction leads to a smoother softmax, and therefore the model will be prevented from easily overfitting. The flow of the training is that the temperature makes a smooth softmax. The loss computed forces the model to produce a sharper softmax next time. However, since temperature is used throughout training, this will be thwarted, and this endless cycle will continue till convergence. It is also important to note that during decoding, especially when using beam search, temperature should also be used during decoding time. We conducted experiments to determine the utility of softmax tempered training. We experimented with low resource settings using the Asian language tree bank dataset, which contains 18,000, 1,000, and 1,000 training, development, and testing pairs approximately. We focused on 11 Asian languages and worked on English to Asian and Asian to English bilingual translation. We did do experiments for high resource settings using the WMT 2019 English to German translation task, but we do not give the results in this presentation. So please check our paper for more details. We perform pre-processing for some languages such as segmentation of Japanese, Chinese, Khmer, Lao, Myanmar, and Thai using an in-house segmenter. We use the tensor to tensor version 1.14 for our experiments, where we use the transformer base for the ALT dataset with a vocabulary of 8192. We trained all our models on a single GPU. Once again, I'd like to remind you that we do use label smoothing of 0.1 by default, and why mentioning this will become clearer in the latter part of the presentation. We experimented with softmax smoothing temperatures, which range from 1 all the way up to 10, where 1 is default, means no smoothing is done. we perform training till convergence on the development set blue score. And this blue score is also the evaluation criteria that we report in this paper. As for choosing the model for decoding, we first average the last 10 checkpoints. We decode the model with the temperature used during training, and we report models with optimal temperatures where we find the temperature that gives the best possible performance. This optimal temperature is determined according to the model that gave the best greedy development score. Note that greedy and beam scores are correlated, and we could have used beam search scores to determine the optimal temperature, but this would involve us determining optimal beam search parameters as well, and that would be too time consuming. And therefore, because greedy and beam search scores are correlated, determining optimal temperature using the greedy search blue scores is sufficient. Once the optimal temperature model has been determined, we then do a grid search over the beam sizes and length penalties in order to identify the best configuration for beam search. Now let's go over the results for low resource settings. Firstly, if you look at the untempered model or the default model without any temperature, we have some performances ranging from very low blue scores in the low 10s to high blue scores in the 30s, depending on the language pair. Next, if you look at the results for what happens when we use higher temperatures, then you can see softmax tempering definitely improves the performance. And if you look at the optimal temperature, aka the temperature which gave the best possible performance, then these optimal temperatures ranged in the values between 3 to 5. This means that by making the softmax very smooth using high temperature values during training is very beneficial for low resource settings. And you can see in most cases, the performance improvements are up to 2 blue points, which is statistically significant. Now let's look at what happens to the blue score and its variation with temperature. We reported scores for Malaysian English and Indonesian English. We varied the temperatures from 1 to 10, as we have mentioned before. And what you can see is for temperature ranges between 1 and 2, there is a slight improvement in translation quality. However, for temperature ranges between 2 to 5, the best possible performance is observed, and the peak performance is observed around temperatures of 3 to 5. Finally, if we increase the temperature beyond 5, we start observing drops in performance because the softmaxes are overtly smooth and the gradients are quite large. Now, once again, you have to remember that we multiplied the loss by the temperature that we use. And therefore, higher temperatures means the loss is also multiplied by a higher value, which definitely affects the gradients that are being computed. Now, having established that softmax tempered training is useful, we wanted to determine its relationship with other smoothing approaches, and especially to determine whether it is compatible with other smoothing approaches. Which other smoothing approaches am I talking about? It's label smoothing and softmax entropy maximization. Now, in softmax tempering, we had the original approach where we took the softmax of the logics, in the softmax tempered approach where we divided the logics by a temperature and then computing softmax. When it comes to label smoothing, the original way for computing labels, for producing labels for loss computation, is to have a 1 corresponding to the vocabulary position for the correct, if it's the correct vocabulary to be predicted, else 0, which is a 1 hot label essentially. In the smooth version, we give a small weight to the incorrect vocabulary items. And therefore, this kind of smoothing or label smoothing forces a slightly smoother softmax. The third approach is softmax entropy maximization, where we have a regular softmax cross entropy indicated by log of probability and indicated by the inner product of the log of the probability and the label. But we also have the softmax entropy itself, which is computed by the inner product of the log of probability and the probability. The entropy, if we increase the entropy, then we essentially are forcing the distribution to become more smoother and more uncertain. And therefore, if we take a linear combination of the softmax cross entropy and the softmax entropy, then we incorporate some amount of softmax entropy maximization during training. And ultimately, our question is, are these three methods complementary? Firstly, let's look at the results of what happens when each method is used independently of the other. So the first figure shows that if we shows what happens when we increase the temperature, keeping label smoothing and no softmax entropy maximization. As you can see, increasing the temperature has a positive impact. On the other hand, when the default temperature of 1 is used, but label smoothing value increases from 0 to 0.5, once again, we can see that translation quality improves. Finally, if the entropy maximization loss weight is increased from 0 to 0.5, keeping a label smoothing value of 0.1, which is the default, and no softmax tempered training, then we can see that as the entropy maximization loss weight is slightly increased, the performance also improves. So independently, all these methods have a positive impact on low resource training. But what happens together? Now, if you look at these results, you can see that these methods are complementary pairwise. In other words, temperature and label smoothing are compatible together to a certain extent, where when we have a temperature of say 5 and a label smoothing of say 0.4 to 0.5, then we get the best possible performance. When we perform label smoothing and softmax entropy maximization together, once again, a high label smoothing value of 0.5 and softmax entropy maximization weights between 0.1 to 0.3 tends to have a strong impact on quality, but not as much as temperature and label smoothing. Ultimately, it turns out if all three methods are to be used together, the softmax entropy maximization method ends up being redundant. In other words, the combination of temperature and label smoothing is the best. So these methods are orthogonal to some extent, but not orthogonal altogether. However, what we do recommend is to experiment with all of the combinations, because there is a certain trend that is observed where using the three methods leads to consistent improvements in a number of cases. Now, what happens to the model during training itself? Well, the figure on the right-hand side shows the softmax entropy during training with temperature, and the figure on the left-hand side shows the softmax entropy during training with temperature, and the figure on the right-hand side shows the same softmax entropy during training, but without temperature. We wanted to see if this kind of making the softmax smoother by temperature really does impact the final distribution or not. And you can see that during training, because of division by temperature, the softmax distribution tends to have similar entropies regardless of the temperatures used. But the moment you take this temperature out of the factor, you can see that the models trained with higher temperatures tend to have sharper and sharper softmaxes, as evidenced by their low entropies. In conclusion, we have presented our application of softmax tempering in neural machine translation, especially where we focus on low resource settings. We observed that there is a huge positive impact in low resource settings. On the other hand, although we have not discussed it in this presentation, there is a limited impact on high resource settings as well. And the visualization of our softmax distributions shows that because of using softmax tempering, the softmaxes eventually end up being sharpened. We also performed a study of softmax tempering, label smoothing, and entropy maximization to determine their compatibility, and we observed that they are to some extent compatible. We also observed that entropy maximization is helpful, but the least helpful. In the future, we want to focus on automatic temperature learning and determining optimal temperature for various corpora sizes. Thank you for listening. I'm happy to have any questions.
Okay. Kevin.
All right. Yeah. So my name's Kevin Du. I'll be moderating this session. So feel free to unmute yourself or ask any questions in the chat or raise your hand. So maybe I'll start off by a question for Raj. So it seems like, these are very, very nice results. So it seems like these different methods are helping for low resource, especially in a sense, because it's doing some kind of regularization, right? So
Yes.
My question is, I'm wondering, how does it interact with other kinds of regularization methods like dropout?
So we did some experiments on using higher dropouts. And when we use higher dropouts, the impact of temperature does go down slightly. But we do observe there are some language pairs which benefit significantly, like say 0.8 to 1 blue, which we found to be statistically significant despite using higher dropouts. But it seems that there is an interplay between all of these different regularization methods. In a sense, we say that softmax tempering is one new regularization method which we have, how should I say, we have discovered.
Okay, but you would say you would recommend trying all of them?
I would recommend trying all of them. It's just a new thing that we found, which seems to have an impact.
Okay, thanks. All right, so we have a question from Robin. Robin, would you like to unmute and say your question, or should I repeat it here? Either way is okay. All right, so Robin Schmidt says, which temperature values tend to work well? Is there some range that was consistent across low resource languages?
So halfway through my presentation in the slide where I presented the low resource results, I showed that temperature values between 3 to 5 seem to have seem to be the most optimal temperatures. And this probably is because low resource models tend to overfit rather quickly. So higher temperature values need to be used to disturb the softmax. So 3 to 5 is kind of what we observe.
All right, another question from Ashit. Do you want to unmute?
Yes, hello. This is Machi speaking from Pro Translating. So my question to you would be, did you use an open source NMT toolkit for your research, or did you develop your own one?
We use tensor to tensor for our implementations.
Okay, thank you.
So and in tensor to tensor, we just modified a couple of lines where the softmax temperature is calculated. So minimal changes to the code, basically. Is that okay?
Cool. Other questions? All right. So if not, let's thank the speaker, Raj, and we can go on to the next talk.
Okay, so I'm having some difficulty using my machine right now. Just a moment. I have no idea why all of a sudden something is frozen. Just give me one moment to figure this out. Okay. Oh, it seems I can't open one of the presentations. Why is this? Kevin, if it's possible for you, could you play the next presentation? For some reason, my local player doesn't seem to be working.
All right. It's R11, correct?
Yes, yes. So I'll introduce the speaker. So the next paper is Scrambled Translation Problem, a problem of denoising UNMT, and the authors of this paper are Tamali Banerjee, Rudra Vimurthy, and Pushpak Bhattacharya, and Tamali is the main presenter.
All right, give me 1 second.
And Professor Pushpak Bhattacharya from Civil Lab, IIT Bombay.
Can you all hear this?
I will first
can you hear us?
start with briefly explaining denoising based unsupervised neural.
All right, so I'll back up and restart.
Hello everyone, I'm Tomali Banerjee from Civil Lab, IIT Bombay. The title of the work is Scrambled Translation Problem, a Problem of Denoising UNMT. The co-authors of this work are Rudramurthy V from IBM IRL Bangalore and Professor Pushpak Bhattacharya from Civil Lab, IIT Bombay. I will first start with briefly explaining denoising based unsupervised neural machine translation. Then I will explain scrambled translation problem. Then I will explain our hypothesis and our retraining strategy to solve it. And then I will share some experimental result and then I will conclude. Denoising autoencoders have enabled deep neural network to learn better representation of the input in an unsupervised manner. Incorporating denoising strategy with autoencoders is important as it restricts autoencoder from memorizing the input and helps to learn useful features from the input. DA typically adds random noise to the input and forces the neural network to reconstruct the original input from the noisy version. These noises can be shuffling noise, add, delete, replace noise and or masking noise. Here we focus on shuffling noise. This is a DAE based UNMT approach named Undreamed proposed by R10 et al. In 2018. Here the UNMT models are trained iteratively as a combination of denoising and back translation for each mini batch. Like for each mini batch, the model is first trained with denoising of L1, then denoising of L2, then back translation from L1 to L2, then back translation from L2 to L1, and this process is repeated for some number of iterations. Here the shuffling noise is the noise which was added, and please note that this shuffling noise was added in both denoising and back translation. We identify an interesting kind of error in the output of unsupervised neural machine translation systems like Undreamed. These models can generate correct order but many times fail to stitch them together to form a correct phrase. As a result, words of the translated sentence may look scrambled. We do not find this type of error in newer unsupervised NMT approaches such as XLM. These newer UNMT approaches like XLM do not shuffle input sentences during fine tuning. We refer to this type of error as scrambled translation problem. scrambled translation can be disfluent or fluent but inadequate. For example, if the input sentence is "living better planet for our kids," then disfluent output can be any ordering of these words. For example, kids for living better our planet. But a fluent but inadequate translation will be "living better kids for our planet." At a glance, the sentence may look correct, but it is not, because the meaning of the translation is changed. "Living better planet for our kids" and "living better kids for our planet," the meanings are not same. Disfluent translations can be a problem of LM decoders, but fluent but inadequate translations cannot be corrected by improving LM decoders further, as it is not a problem of sentence generation. Due to incorporating shuffling noise with input sentences, the encoder becomes unable to process ordering information. This makes the model fully dependent on LM decoders to decide the word ordering. It cannot differentiate between encoder representations of "living better planet for our kids" and "living better kids for our planet." We hypothesize that the reason behind this error is shuffling noise, which is introduced in every input sentence as a denoising strategy. To test our hypothesis, we stop the training of the undreamed model after a pre-decided number of iterations. Then we resume the training for the remaining iterations using original sentence as input without adding any noise. If our hypothesis is true, this retraining approach should show improvements over the baseline approach. If the baseline approach is of undreamed, which is n iterations of DAE plus back translation shuffled, then our retraining approach is doing the baseline training the baseline system for m iterations and training the remaining n minus m iterations without adding any noise to the input sentence. We experimented this with language pair English French, English German, English Spanish and Hindi Punjabi. And training data we used NewScroll and Wikipedia dump. Test data we used WMT and ILCI. And BP merge operation is of 50K. Word embedding is word2vec and crosslingual mapping is vecmap, and UNMT tool used undreamed. And we saw that result of undreamed with retraining strategy produces statistically significant improvements. We also analyzed intermediate result, where we saw that our approach leads to increase in blue score in the retraining phase as the denoising strategy is removed. Here the blue line signifies the baseline approach over the different number of iterations, and the orange line signifies the blue scores for different number of iterations using our approach. Here is a sample translation of Spanish to English translation model. Here the English reference is the announcement of the probable discovery, and the model trained with R10 et al. Approach produced the phrase "the likely announcement of the discovery." Here we know that likely is a synonym of probably. So the positioning of the word likely is wrong here, and we can see that when we retrained this with correctly ordered sentence, then the model generated the announcement of the likely discovery, where the positioning of the word likely is correct. We also tested it with n-gram blue improvements. We saw that improvements in n blue, which is n-gram blue, is higher for higher n-gram. Higher n-gram means where n is greater than 1, like for n-gram blue. We got better improvement in case of blue 4 than blue 1, which indicates that there is improvement in phrasal matching. Now, when we observed attention heat map of a French to English translation, we saw that production of word aligned attention distribution was easy for the attention models which we trained on sentences without noise. We also experimented it with XLM, and as we saw earlier, that XLM do not have this problem, and when we applied our retraining strategy over it, we saw that it was not benefited from our retraining strategy. To conclude, unsupervised neural machine translation model which use word shuffle noise in all input sentences, such as in undreamed, can generate correct words but fail to stitch them together to form correct phrases. We named it scrambled translation problem. Often these models generate fluent translations with wrong meaning. It indicates that the problem is not with LM decoders. We hypothesize that the reason is word shuffle noise, which was introduced in every input sentence during training as a denoising strategy. To test our hypothesis, we retrained the model with sentences of original word ordering as input, and we observed that the retraining solved the problem. Thank you.
Okay, that was a very nice talk. Tamali, are you there?
Yes.
Okay. If anybody has any questions for Tamali, then please feel forward to raise your hand or type it in the chat. In the meanwhile, I have a couple of questions. So one thing is interesting is that the shuffling or scrambling based denoising objective seems to actually create a wrong expectation between what the actual word order is supposed to be versus what word order the denoising approach is trained on. So do you think that auto-encoding is even necessary? Or why not just, after training for a fixed number of steps, why not just resume with back translation based training? Do you have any comments on that?
You mean just stopping denoising from the beginning, just
Yes.
not adding any noise. We experimented that, but our preliminary results suggest that there the training is not happening correctly.
Not from the beginning, which means you do denoising based training for the first fixed number of iterations, and then when you do the continued training on auto encoding, but instead of having auto encoding, you just don't do that at all, because auto encoding tends to basically learn a trivial mapping. So I'm wondering if auto encoding is really necessary. Just use back translation. If you have any comments, if you have any intuition on that right now.
No, I have not tried only back translation, so I cannot comment on that.
Okay, that's fine. That's fine. Then the second question, if anybody else does not have any other questions, I have another question. Did you, so you train for a fixed number of steps using denoised autoencoder training, right?
Yes.
What was the criteria for how did you decide those fixed number of steps? Did you do that on convergence in the dev set by any chance?
We checked the perplexity, and when the perplexity was like it converges, we stopped that. And
okay, So what is your convergence criteria?
So it was we was checking the perplexity change. So right now I can't remember the exact change. So we were stopping when the change is not very much for
Okay.
a longer sequence.
Okay, that's fair enough. And when you stopped, when you finished your initial steps of DAE training, and then you resumed training on AE training and back translation, did you reset the optimizer, or did you just continue using the previous optimizer state?
So the in number of iteration was nearly 6 lakh.
Okay.
So when we used our approach, we took half of that for denoising.
Okay. So you did not reset the optimizer or the learning rate at all.
We trained it that again.
Okay, fair enough. Okay, so that means you probably reset the learning rate as well. Okay, that's good. Kevin has a question. Kevin says, your method makes me wonder, are there different kinds of shuffling approaches possible, like all words versus neighboring words? Do you have any comment on that, Tamali?
In this experiment, we did the neighbor shuffling, but I don't know how it will perform for all kind of set shuffling.
Is that okay, Kevin?
Yes, thanks.
Okay. So I'd actually like to build on top of what Kevin asked. What do you think about doing shuffling of like linguistic phrases? Like if there is a noun phrase, if the sentence is segmented into different types of noun phrases, verb phrases, and then do shuffling of those, do you think that might be a better shuffling objective, or have you considered trying that?
Again, when we tried that, it did not improve from our preliminary experiment, so we did not go in that direction.
Okay, fair enough. Okay, so that's about time for this paper. Everybody, let's thank Tamali for her presentation, and let's move on to the next one. The next presentation is, just a moment. Yeah, the next presentation is Make the Blind Translator See the World, a novel transfer learning solution for multimodal translation. The authors of the paper are Minghan Wang, Jiaxin Guo, Yimeng Chen, Changshu Minjiang, Shimin Tao, and Hao Yang. I'm sorry if I've mispronounced your names. And the first author is Minghan Wang. So let me first play his presentation. Just a moment. Okay. This one. Kevin, can you see my screen?
Yes, I can see your
Awesome.
screen.
Hello everyone, I'm Wang Minghan from Huawei. Today I'm going to introduce our work in the MT Summit. The title is Make the Blind Translator See the World, a novel transfer learning solution for multimodal machine translation. And I'm going to introduce with following 4 steps. First, what is multimodal translation? Multimodal translation can be defined as leveraging information from multiple modalities to perform machine translation. There can be many applications. For example, with the text and visual inputs, we can perform image description translation, or with the visual or speech inputs, we can have video translation. And in our work, we focus on the first task, which is the image description translation. And in this task, this task was first proposed in the work of Lucia Spezia in 2016. And in this task, we are going to build a model to translate a source sentence into the target language with the help of an image. And the motivation behind it is to make the model to have better understanding with additional context or for word sense disambiguation. And the task is also used as the shared task of WMT 2016 to 2018. and we're also going to compare our results to participants of the shared task. And in this task, we are going to use multi-30K dataset. The dataset contains two language pairs, which are English to German and English to French. Both of them contains about 32,000 of sentences, which average length of 12 tokens per sentence. And the dataset has been split into two test sets, where our model will be evaluated on them. And we can make a conclusion that the dataset has limited sets, but is clean and short. And in our work, we are going to use blue and meter as the evaluation metrics. And now I'm going to introduce the method in our work. The first thing for us to do is to create a mono-model baseline. Since the dataset contains limited instances, we choose to use the strategy of pre-training and fine-tuning instead of training the model from scratch. Therefore, we pre-train two standard transformer models on the WMT19 English to German and the WMT14 English to French news corpora. And then we fine-tune them on the text data of multi-30K. And as you can see that the pre-trained model has already got good performance on both languages. And after fine-tuning them, they obtain additional improvements, especially for the English to French direction. And then we start to think about how to integrate visual information into the model. Actually, we bring the concept of transfer learning. Instead of transfer knowledge between domains, here we want to perform transfer learning between modalities. That is, first pre-train the model on the mono-model dataset, and then we are going to add some visual-related components to make the model to be able to encode visual information, and then fine-tune the model on the limited multimodal dataset. And we call the model as a VL transformer, which means the combination of vision and language. And here is the detail of the model. We use an intuitive but effective way to combine two modalities, which is to concatenate both inputs into one sequence and use the self-attention of the transformer encoder to perform interaction or fusion between them. And however, the model has to distinguish between the input of modalities. Therefore, we introduce the modality embedding to them, and 0 is for the text input and 1 is for the visual input. Then I'm going to introduce the visual related components, which are actually 4 linear transformations. And since we are using the bottom-up and top-down attention proposed in by Anderson, and this network was pre-trained on the visual genome dataset, and we actually use it to perform feature extraction by firstly detecting objects in the provided image and collect the top 36 detected objects, and then extract features of each object. And the features includes the ROI feature, the bounding box coordinates, the class label, as well as the attribute label. But they have different dimensions. Therefore, we use 4 linear transformations to map them into the same dimension and sum them together to get the feature vector of in an object level. Finally, we will have 36 object or feature vectors, and we can concatenate them after the token representation. And now we can fine-tune the model on the multi-threaded key for both modalities. Before fine-tuning, we initialize the newly introduced parameters randomly and initialize the remaining parts with the pre-trained transformer, with the parameters from the pre-trained transformer. However, after pre-training, we find that the model only obtains limited improvements, and we want to investigate what happens. So we collect the attention map, the encoder-decoder attention map from the model, and we swap the index between the image feature and the text feature for clear presentation. And as you can see, that the model almost entirely ignore the image feature and only use the text feature to make prediction. Therefore, we assume that when the pre-trained model is strong enough, the model is likely to ignore visual information. To solve it, we propose the cross-model masking. The intuition behind that is to encourage the model to use complementary information. And how to use that? For example, during training, for each sample, we will first select a modality to inject noise with the probability of 50%. For example, if we are going to choose the text input to inject noise, we are going to further select elements from this modality with the probability of 15%, which is similar to the masking operation in BERT for mask learning model. And if we are going to use the visual modality, the element to perform masking will be replaced by a noise vector sampled from a normal distribution. And in this way, the model is forced to use the other modality to make prediction. Okay, now I'm going to introduce the experiment. So here is the setup of the experiment, and I'm going to pass it. And here is the performance. So from this table, we can see that the Veil transformer with cross-model masking obtains consistent improvements compared to the model trained without it. And actually, we are curious about what happens when we use cross-model masking to train the model. So we took an interesting experiment. In the experiment, we first select an image from the dataset where the English description is two dogs are playing together on green grass, and we use the text and the image as the inputs and use the model to make the prediction without any noise, and we collect the attention map. And as you can see, the translation Swihand has already correctly aligned with the detected objects, two dogs, as well as the two dogs tokens from the source language. And this has already demonstrated that the model has ability to use both modalities to perform translation. After that, we deliberately replace the dogs token with an unknown symbol, and we want to observe what happens after we performing like this. And we can see that the model gives larger weights to the detected dogs, to the detected objects, which are two dogs. So this means that the model is able to use auxiliary modality as the information source, and I think this demonstrates the effectiveness of the cross-model masking. Okay, now I'm going to make a conclusion of our work. So first, we propose the VR transformer to perform transfer learning from monomodal to multimodal, and then the proposed cross-modal masking demonstrates its efficiency on learning the cross-modal interaction. Finally, the model obtains competitive performance on multi-30K dataset. That is all for our work. Thank you for your attention.
Okay. Oh, okay. So that was a nice presentation. Are the authors here by any chance? Please unmute yourselves if you're here. I have some questions, and maybe someone from the audience also has questions. Is anyone here? Minghan or Jasin or anyone? No one? Okay, looks like the paper presenters probably have not attended MT Summit. Okay, I guess then there's no choice but to move on to the next paper. But if anybody has any questions, then please write them down in the chat, and maybe Kevin or I can forward them to the authors, and maybe they can get back to you. So yeah, that's one possibility. In any case, I'll be moving on to the next presentation. Does Steve want to say something?
I was just going to say we can't really move on until the 8 o'clock.
That's right. That's right. Okay, so then we have 7 minutes. I guess we have no choice but to wait.
Unless there's some discussion about this multimodal MT. Is anybody else doing multimodal MT? And have you had any positive experiences with it? Have any of the attendees here participated in that?
Yeah, I think it's a fascinating field. Lucius Bessie has done a lot in this area. And I think we'll hear more about it later in the keynote. So I feel like, it's just my personal opinion, I feel like multimodal could mean many things. You could have multimodal in the case where your video or your image and the text input are about the same thing, but you could imagine like for example, like image captioning kind of problems, where your caption is actually talking about the image. But then you can also have cases where they're not very related, right? So maybe a TED talk where the person is talking about some subject, there might be some images on the screen, but it's related, but it's not exactly the words that person is saying. And so I feel like there's a range of problems. We call them all multimodal, but maybe underneath they should be treated differently. Anyways, it's just my thoughts so far. Anyone feel free to jump in. I think this is we're doing sort of a hallway chat now, right, Steve and Raj?
Yeah. So I've something to say. So there was this paper last year on simultaneous multimodal translation, where the modality seems to be more helpful when you have a simultaneous translation setting. So I think focusing on that might actually open up some nice, interesting directions. And then maybe, how should I say, data to text scenario, where you have a table and then you want to describe the contents of that table in another language. Maybe that could be one additional modality where we consider, where we may have a description in English, we have the actual table, and then we might want to also have the translation of that English sentence into some other language. So I wonder if that can also be considered as a modality.
Yeah, and I guess the cool thing about multimodal these days is everything is a neural net. So it's not too hard to get into field. I remember 10 years ago, I was trying to read some computer vision papers and I just didn't understand any of the vocabulary or terminology of the papers, but now it's all the same terminology.
I mean, it's a CNN which learns the filters. So of course, I suppose there are more advanced methods, but I feel much more comfortable just stitching some image encoder and text encoder and then feeding it to the decoder. Probably 10 years ago, that might have been a nightmare.
Yeah, they require training in the PhD to do that. Now you just download something.
I mean, we have to thank Hugging Face as well. It's just a couple of lines and then we automatically get this classifier, which we can use very easily.
So I wonder if there's ever been any work done on modalities other than text and then visual, right? So what else could there be, right? Sensory input. There's hardly any data, right, to use. But I was just wondering. I mean, multimodal as humans, right? We have all of our senses to help us disambiguate to situations.
Yeah, that's interesting. So you, I guess we do what we have facial gestures. Okay, so, yeah. So she said pitch and stress. That's true. Yeah.
So yeah, the pitch and stress thing is interesting. I mean, so you've got audio, right? That so if you've got some written text, often the written text isn't the ambiguous part. It's the speech that's more ambiguous. Well, but again, I don't know. You could have the audio helping you translate the text and vice versa, right? To get it right. So I like the comment about the video recordings that was made here in the chat a minute ago. Video scripts, right? I mean, so again, you're watching a video, right? And there's a context. You're in a house in a room, and somebody picks up something, or points at something, and that's the kind of thing that you would really want the multimodal MT to be sensitive to, if that were possible. But anyhow. Okay, well, it's a minute to end now. You want to introduce the next person, and they can start right at.
Yep, I'll get to it. Okay, so the next paper is sentiment preservation in review translation using curriculum-based reinforcement framework, and the authors are Divya Kumari, Soumya Baswaraj, Nikesh Garera, and Asif Iqbal. I'm sorry if I've mispronounced anybody's name. And I think the person who will be speaking is Divya Kumari. So let me present their paper. Okay, there you go. This one.
Hello everyone. Welcome to the presentation entitled Sentiment Preservation in Review Translation using Curriculum-Based Reinforcement Framework. My name is Divya and I am PhD student at Indian Institute of Technology, Patna, India. I, along with my co-authors, Soumya, Nikesh, and my supervisor, Asif Iqbal, who is Associate Professor in Department of Computer Science and Engineering, Indian Institute of Technology, Patna, would like to present our latest research in the field of sentiment preservation in the machine translation of a review text. First of all, I would like to highlight some of the use cases of an MT system, and then we discuss about how these possible use cases brings motivation for this piece of work. So in a cross-lingual context, the possible consumer of an NMT system is either human or a downstream NLP application. So depending upon the end consumer of the translated text, the MT system should pursue the objective of preserving those properties of the source text that is relevant from the point of from the consumer point of view. What I mean by saying so is that, for example, when the consumer is a human, then the quality criterion of an MT system relevant to human is generating a fluent and an adequate translation. However, this criteria might not be the optimal one when the end user is a machine. For example, when the MT output is used as a training or a testing set of a cross-lingual sentiment analyzer, then encoding the correct sentiment of a source text to the target became more important over the adequacy and fluency, as the classifier performance is highly dependent on this trait of the input text. So taking into consideration these use cases of the NMT system, when we looked into the literature, we found that several work has been done where the focus were laid either on the preservation of a human-oriented criterion or on the preservation of a machine-oriented criterion. So unlike this previous work, in this piece of work, we try to adapt the parameter of a fully developed NMT system so that the generated translation can further improve the quality of a translation as measured by the BLUE score, along with the performance of a cross-lingual classifier as measured by the F1 score. So the main use case scenario for this piece of work is that the translation obtained by the adapted NMT system can serve to its best to both human as well as to the machine. In this slide, we discussed about the basic architecture of the vanilla actor critic framework, which in the latter slide will be used in conjugation with curriculum learning to fine-tune the parameter of a fully developed MT system so that the generated translation successfully encodes the underlying sentiment without compromising its adequacy. So this actor critic framework actually has three main components. The actor to the left, the critic to the right, and this reward module below the critic. So these are three main components. Here, the actor is a pre-trained neural NMT agent, neural agent that is the NMT system, whose parameter defines the policy here. So this agent takes action based on its policy. To train this actor in the RL fine-tuning step, we use the policy gradient loss, which is weighted by this reward component R tau, which is basically calculated as follow. There is this reward, which we will discuss in the latest stage, how we obtain this R. And this which is then being subtracted by this V component, which will be given by the critic model obtained from the prediction of the critic model. So critic will predict this value. So this V component is what distinguishes it from the normal reinforced loss. In a reinforced loss, we do not have this V component, whereas in this actor critic policy gradient loss, we have this extra V component for sentiment. The second important component is this reward model. So it's basically a score function R, which we also refer to as a true reward, which is used to evaluate the goodness of the policy. So in our case, to ensure that NMT learns the policy that guarantee the preservation of sentiment and semantic in translation, our reward module gives two constituent reward. The first is sentence level BLUE, and another is this classifier based reward, which is being calculated by taking element wise dot product between the predicted sentiment distribution, which is obtained from the softmax layer of the classifier, and the goal sentiment distribution. And so this component basically ensure that the sentiment is preserved, and this another component is to ensure that the content is preserved. And finally, to achieve that both the content and the sentiment is preserved in the translation, we take harmonic mean as a final reward R, which we refer also as a true reward. The third important component, which is a critic, is a deep neural function approximator that predicts an average estimated reward for the action. So to train this critic, we use MSE loss that's calculated between the true reward that we discussed in step 2, how we obtain this true reward, and the critic estimated value, that is V. This is being predicted from critic. So subtracting this critic estimated reward from the true reward actually helps actor to identify those actions that brings it a reward beyond the expected return. In this slide, we discuss about the curriculum we use to define the difficulty of the training samples. So let's say there are total n RL training samples. So to calculate the difficulty of say ith training sample denoted by xi or the tuple SI-TI, where SI is the source sentence and TI is the reference translation, and one more notation T hat I that represent the corresponding sample translated output of the source translation. So once we have this SI-TI or T hat I pair, what we obtain is that the corresponding harmonic reward for these data points on the as recorded on their translation, and we repeat this process for all the n data points. Once we have this harmonic reward for all the n data points, we sort this RL training sample in an easy to hard fashion, where easy is considered those that have high harmonic reward, and the hard are those samples that has low harmonic reward. Finally, in this slide, we summarize the whole training process, which can broadly be divided into 3 steps: the pre-training, curriculum construction, and the actor critic fine-tuning. So firstly, we pre-train both the actor and the critic model using the supervised parallel training samples. Then we use the pre-trained actor to translate all the RL training samples and calculate their corresponding harmonic reward using these translated samples. Once we have obtained these reward for all the RL training samples, we sort them in an easy to hard fashion, and which is later used in the fine-tuning steps of the actor critic framework, which we already discussed in the previous slide. So our experiment was performed across 2 language pair, French English and English Hindi. Also, as our experiment are performed in terms in the 2-step process, the pre-training followed by fine-tuning. So the data set that we used in the pre-training step, we refer to them as MLE training data set, and the data set we used in RL fine-tuning that we refer to as RL fine-tuning data set. So basically, this RL fine-tuning data set is a subset of sentences derived from this MLE training data set itself, but now they are additionally annotated for their sentiment. So for French English task, the data set this data set is a composition of 2 publicly available corpus. The first is a 4-square corpus, which is a small parallel restaurant review data set released as a part of review translation task. And the second one is an open subtitle movie review corpus. The reason we choose this corpus is that it's made of a spoken language sentences, which is noisy, sentiment rich, and is closest to 4-square corpus. And in the English Hindi task, we used our newly created domain-specific parallel corpus, whose sentences were sampled from an e-commerce site, Flipkart. The detailed statistic of this data set is presented in Go2. So here, first we will discuss our results for the vanilla actor critic approach, that is without curriculum learning. So we can see that for both the language pair, French English and English Hindi, the blue score improved significantly over the supervised baseline in both the language pair, and the same goes for F1 score as well. And when we compare it with the curriculum-based approach, we see that curriculum brings improvement further even over the vanilla actor critic approach. But this was only for the blue metric. For the F1 score, we observe a slight drop in the performance, but still it maintained a significant high performance over the supervised training in the sentiment task, and the best performance in the machine translation task. And if we compare our proposed approach with the other baseline, for example, machine-oriented approach, where the reward function being maximized was the classifier performance, and the reinforce, where the usual practice being followed is to optimize the blue score in the empty scenario. So for when we compare with these two cases, we see that the optimized metric improved, but this was not the case for the non-optimized metric. For example, in MO-reinforced, optimized metric was BERT. So for both the optimized metric was F1 score. So for both the language pair, we observed an improvement in the F1 score. But the non-optimized metric, that is blue, we observe at least for French English a drop in performance, similarly a non-consistent behavior was observed for reinforced based approach, where the optimized metric was usually being used as a blue. So for that also we observed that for one language pair the blue score improved, for other there was slight drop in performance, and similarly for F1 score there was not consistent improvement. For one there was an improvement, while for other there was a drop in performance. While a consistent improvement was observed over the baseline, over the supervised baseline with our actor critic approach. So in this slide, we conclude our work in the two language direction, French English and English Hindi. Our experiments show a further improvement again in the sentiment preservation and machine translation task over a fully developed NMT system with a parallel data cost in added. And also the output obtained from this fine-tuned NMT can be used to serve its best to both human as well as a machine. And introducing curriculum further result in a better convergence over the vanilla actor critic approach. And at last, in this work, we also introduced a new domain-specific product review polarity level balanced bilingual corpus for English Hindi. Thank you.
Okay, that was a nice presentation. Is any of the authors over here? Divya, are you here?
Yes.
Okay, so we have quite some time for questions. So if anybody has any questions for Divya, please feel free to ask. You can type it in the chat, or you can just unmute yourself and ask.
All right, maybe I'll unmute and ask my question, if that's fine. So Divya, I'm very curious about your data set. It's very exciting to have this kind of bytext with sentiment annotations. I think that really helps us explore problems where MT is not just producing for human consumption, but also for some other application. So I'm curious, can you talk a bit more about how your Hindi data set compares with this existing French English bytext that's been released for restaurants? Sort of qualitatively, what are the similarities, what are the differences? And secondly, if your data set is publicly available, it'd be nice to know where to get it.
Hello?
Yeah, Divya, we can hear you. Please go ahead.
Yes. The difference between already available French English dataset and our newly introduced dataset is that it's from product review domain, whereas the earlier data already existing French English dataset is from restaurant domain. So although both are, if we look at the data set, both are in terms of, if we look at in terms of sentiment, both are sentiment rich. While one discuss about the reviews from restaurant domain, while our email introduced discuss these reviews from the product domain. And as far as making it publicly available is concerned, yes, we will make this data set publicly available for research, along with the source code that we used in our experiment. Thank you.
Oh, thank you.
Divya, I have I went through your paper, and you didn't mention anything about the future scope of this work. So could you comment on what the future steps involving this line of research can be?
Actually, we are working on the future direction of this work, and the paper is under review. So one more extension was that in this piece of work, we actually experimented with the basic RNN architecture. So we were curious about how this actor critic method actually go with the transformer architecture. And also it was in this paper, we experimented in a low resource setting where we observed actually that even with the same data set, we can achieve a further improvement using this RL technique. So it means no additional parallel data cost being added. So we were looking into things like what if we can take this example in an out of domain in domain scenario. So we have this kind of future work that we can do, experiment with the transformer, then under different setting like in domain, out of domain setting. So we can go in that direction.
Yeah, that's interesting. Thank you. So just one small question from me again. So then if you said that you just you use the RNN method and not the transformer, then probably do you have any plans of using these existing pre-trained transformer models like BART or BERT to then fine tune and maybe get very high blue scores? Do you think that the current limitation of your work is because you use an RNN method and without any kind of pre-training?
Sorry, but in this current piece of work also, we actually first did this pre-training part where the NMT was fully developed, and that was followed by fine-tuning.
Yes, but
yeah.
The pre-training was done on which data, by the way?
On this French English dataset that is publicly available, and also a newly introduced English Hindi dataset.
Okay. But I mean, what I meant was these data sets are quite small. So I wonder what would happen if you used much larger data sets.
Yes. So we are also currently looking into that how things goes on if you have high resource scenario. So we are experimenting on that as well.
Okay, that should make for an interesting observation. Okay, thank you very much, Divya. And yes, Kevin has a follow-up question. Kevin, is it okay if we speak about this during the extended Q&A session?
Yeah, that's fine.
Okay, awesome. Okay, then let's move on to the final paper of this session. The final paper is titled On Nature and Causes of Observed MT Errors by Maya Popovic. So I'll start her presentation video, just a moment. Okay, there we go, share screen, and we'll see. Okay, next.
About nature and causes of observed machine translation errors. So usually machine translation errors are analyzed either by marking them or classifying them, which means marking them and assign a predefined category to each of the error, or identifying nature and causes of these errors, which are then usually used by building a test suite for identified phenomena. And then in this work, we are trying to identify nature and causes of errors which were previously marked. So that was carried out basically in two steps. So first step was marking errors, and then second step, identifying causes of marked errors. So there are no predefined schemes. So identification of phenomena, usually linguistic phenomena related to the observed errors, was carried out on the fly. And we didn't create any test suite in this work, but it would be an interesting direction for future work. So we used two publicly available datasets which contain marked translation errors. One is DCU set, which was created for purposes of MT evaluation directly. And the other one is provided by Heidelberg University. So it was used for improving NMT system by learning from marked errors. So it was not used directly for evaluation. So the DCU set, it contains English to Croatian and English to Serbian user reviews, translated by 10 different machine translation systems, and then errors were marked by 15 evaluators. And there are actually two subsets, adequacy errors and comprehension errors. So two quality criteria were used for this data set. And the annotators were also asked to separate major and minor errors to distinguish. And then Heidelberg dataset is English to German TED Talks, only one empty system, which was improved, 10 evaluators, and the quality criterion is not specified. So it's usually related to mixture of adequacy and fluency, but the annotators were only asked to mark errors and nothing else. And they were also asked not to mark omissions and rewording errors because of the loss function, which were used for improvement. So the statistic of datasets can be seen here, a number of segments, a number of empty systems, quality criterion, and a percentage of marked errors. So after our analysis, we found out that the most frequent phenomenon are these. So most of the marked errors are related to some of those phenomena. And it's similar for all data sets, which is interesting. So basically rephrasing, ambiguity, noun phrase, and mistranslation are common for all, although there are quite some differences between data sets as stated previously. And then there are some examples of the most prominent errors, which maybe are not completely clear. So the rephrasing is then when the translation actually follows the source sentence, and then it's not a good translation because it's not even a literal translation, it's just following the source sentence without any really context. So it's then full of errors, and then it can be perceived in different ways. And then noun phrase errors are similar, but they're restricted only to basically English noun phrases, so the sequence of nouns and adjectives. So major versus minor errors. We also wanted to see which phenomena are related to minor errors and which to major errors. So although some of the phenomena are really much more frequent than others, frequency is not necessarily related to the importance or severity. So we analyzed all observed phenomena, although the results for the less frequent phenomena might not be sufficiently reliable. So here is one horrible table, but the full numbers. So these are all identified phenomena, but the point is here that some of the phenomena are clearly more related to major errors, some of them to minor, but some of them, especially those with which involve a lot of words like noun phrase, rephrasing, also negation, they are more or less equally distributed over major and minor errors, and then some words are even perceived as correct within a negation or rephrased group of words, and so on. So why is this interesting? Because first of all, the severity of errors is perceived differently for different phenomena. And then the other thing is that perception of some phenomena also depends on the quality criterion. For some, for example, for adequacy are maybe more like major errors, and for comprehension was more like minor errors. So therefore, we were motivated also to investigate a little bit more this mismatch between adequacy and comprehension errors. So we analyzed these discrepancies, which were marked by the same evaluator, but also by two different evaluators, because each empty output was marked by two different annotators. It was possible to do with this U set. And then why to do that for two different evaluators? Because in order to evaluate two criteria, so one evaluator has to first finish all comprehension errors and then to mark adequacy errors, because for comprehension errors, they must not see the source text. And then if two different evaluators are working, they can work at the same time. And also monolingual evaluators can work on comprehension. So the results, which will be shown now, so the discrepancies between adequacy and comprehension errors are a little bit larger if there are two different evaluators, but the tendencies are the same. So it would be possible to facilitate evaluation of both criteria by recruiting more evaluators, different evaluators. So here are actually the most prominent, the most frequent phenomena, and also most interesting phenomena, because we can see that some of them So this is discrepancy between adequacy and comprehension, like inadequate comprehensible words and vice versa, because it means that the people understand that, but it's not the correct translation. Or adequate incomprehensible words is that the translations are correct, but the people don't understand what the translation wants to say. And then for non-existing words, untranslated words, and some errors in the source text, so adequacy and comprehension are pretty similarly observed. But then for some other criteria, although they're rare, or phenomena, although they're rare, but it can be seen that the discrepancy is very high, especially for omissions, but also hallucinations, mistranslation, conjunction problems, and negation problems. And then also rephrasing, ambiguity, and noun phrase, more or less something in between. So why is that interesting? So all in all, it's like 1/3 of adequacy errors seem to be comprehensible. Like if the reader reads it, they think everything is okay, they understand, but it's not correct. And then on the other way around, so more than 40% of the words that the reader doesn't understand while reading the pure translation are actually adequate translations. So when you look into the phenomena, so as we said, so there are some similarities, like for source errors, non-existing and untranslated words, they are similarly observed by both translation criteria, quality criteria, and omissions, hallucinations, negation, and conjunctions are perceived very differently. So omissions, obviously, because if you don't see the source text for comprehension, you don't know what is really missing for the source text, so something else might be seeming missing, which is not. And then hallucination is the case when the translation is not at all related to the source, which means that adequacy is practically zero, but it often seems comprehensible if you don't see the source text. And then negation and also relative clause with conjunction. So these are large span phenomena involving a lot of words, maybe the entire sentence. So then discrepancy is often related to this large span because for comprehension, some other words might seem as errors than when you see the source text and then see what actually is going on. Some examples of conjunction or relative clauses here, like often in English, the conjunction is missing, and then translation is also missing, but then several words are actually incorrect. And then on the other hand, sometimes the conjunction is not needed. There is no relative clause, but in translation is made like it was relative clause, which is also not good, both in Serbian Croatian as well as in German. And the negation, like negation span can be rather different. Like in the first example is only this never liked any, but then in the second the whole phrase is actually observed like incorrect. And then in the German example, there is only negation marker missing, but still. So the span can be quite different. So in total, so we find out some very frequent phenomena which are causing machine translation errors in modern systems, which are basically rephrasing, ambiguity, noun phrases, and mistranslations. And then furthermore, we find out that perception of errors is definitely dependent on the quality criterion. So what guidelines you give the annotators, just mark errors or adequacy or comprehension or something else. And then ideal evaluation would include both adequacy and comprehension. Comprehension is, in our opinion, more important than fluency. But we are aware that evaluating both is time and resource consuming because for comprehension, you cannot see the source text, so it cannot be assessed in the same time, while adequacy and fluency can be assessed in the same time. But our findings are showing that it's possible to facilitate that by involving different evaluators to work on different tasks simultaneously. And also it is possible to evaluate comprehension only by monolinguals.
Okay, that was quite a nice talk. Maya, are you there?
Yes, I am.
Okay, so if anybody has any question for Maya, then please feel free to unmute yourself and ask, or just type your question in the chat.
Hi, this is Kevin. Yeah, I'll start off with a question. So I think it's very, very fascinating. You have all these different kinds of error types. I'm wondering how often do you see a single sentence having multiple types of errors? How correlated are these, and how difficult it is to tease them apart sometimes, or it's fine to treat them all separately like this?
Okay, so like these large span errors are actually something where so many things went wrong and you cannot say like this rephrasing. So it's so many different types. For example, there might be also lexical error and morphological error and all together. And then all of that is actually because it failed to rephrase. So some of these categories are precisely comprising several pure error types. And then, for example, if we say gender, it's just purely gender went wrong and nothing else.
Mm-hmm.
So you could see exactly the word where gender went wrong. And then you might have also gender in those rephrasing, but it's such a mess that it's really something beyond that. So I hope that answers your question.
Yeah, thanks, Maya.
There's a question from Alberto. I may have missed that part in your annotation. Do you have the specific fragments marked as errors, or is it an annotation at the instance level? If the answer is fragments, have you released it?
So do you mean, do I have some words span, like number of words which should be annotated, or I'm not sure that I understand.
Hello, can you hear me?
Yes.
Yeah.
Yes, I mean precisely that. So rather than just saying in this pair of sentences, for instance, there is this kind of error, I was wondering if you have highlighted the specific fragment that composes that error, because that would be very interesting.
No, so the annotators were free to do. So the idea behind that is that, I mean, the goal of the whole thing was to analyze the types which are bothering people, like to say that. So either by just reading, like the user, for example, doesn't care about source language and just reads the translation. So that's why comprehension. And then of course adequacy, because if adequacy failed, also translation failed. So the idea is that I didn't give any span, I didn't give any error types, just criteria, like mark everything that you don't understand, or mark everything that it has different meaning than source. So in this sense, the evaluators were rather free, both. So some evaluators sometimes marked the entire sentence, some were trying to really figure out which word went wrong. So there are also differences in span, but overall there were like clear tendencies in these error types. And then if you see, there is also a table in the work itself, so you can see that kind of 1/3 of errors, I mean, it was not really possible to define the cause. I think it's precisely because I gave the freedom. So there were also some preferences, like personal preferences of evaluators, like I don't like this word. So maybe it was not really a bad word, but they just perceived it as errors. But I really wanted not to, any error not to escape. So better over marking than under marking. So that's why it was just like mark whatever you feel like. Yeah.
So let me rephrase very quickly. You didn't give any span to the annotators. Did they give you one? Did they annotate the span? Did they say, I found this error in these 2 words, for instance?
No, I just said mark everything which you perceive as error.
Okay. Okay.
be it
Thank
word
you.
or word group. So whatever you think it's an error.
All right. Thanks.
Okay, so we have a few more questions.
Yes.
So Andy asks, is someone muted? Okay. Andy asks, I know I'm biased, but well done, Maya. What about omissions? People are quite good at guessing what word has been missed out. That, for example, a missing word might not be too harmful for intelligibility. So do you have any comments on that?
Yes, I mean, it is very different for comprehension and adequacy, because people, of course, if something in source is missing, sometimes it might hurt, but sometimes it doesn't hurt. It's just missing and they don't know. But then on the other hand, there's some error which is coming from the source, but it looks like something in the target language is missing. So there are some differences in both directions in comprehension and adequacy. So often they felt that something is missing while they were reading, but that there was nothing really missing. And then often they didn't spot that something is missing in source. So it is different. So the number of omissions is maybe similar, but when you look into what they're marking, it was quite different.
Does that answer your question, Andy? Okay. And then one final question by Evelyn. I also had the same question actually. To what extent can these frequent MT error types be extrapolated to other language pairs?
Well, I guess it also depends on machine translation systems, but so I would say it can be extrapolated well, because I mean, here we had two European languages, I have to say, but also different, three, so two very similar and German, which is different. And then one is like has more resources, the other one has not. So it was also different systems. I'm not sure what the German system was trained on. Maybe it was not fully powerful system, but still. So there were very diverse systems. So we use 5 different systems in one study and then another for German, and then 5 more for Croatian. So online systems and in-house systems. So the diversity in systems was high. Also lower quality, higher quality, and so on and so on. So of course, it cannot be fully extrapolated. Like, I'm sure that in Japanese ambiguity will be a problem, but I wouldn't be surprised that in Japanese also like ambiguity and rephrasing and mistranslations are a problem, to be honest.
Evelyn, does that answer your question?
Yes, thank you very much.
Okay. Okay, so let's thank Maya for her presentation. Okay, so we are done with all of the research papers and the presentations in the QA session. Now we have the extended QA session for all of the papers. So anybody who may have missed the paper session but have questions or had questions during the paper session, but we ran out of time for that paper, please feel free to ask your questions now. I'm also, Kevin, is it okay if we kind of like just open up these next 20 minutes for discussion if anybody wants to just raise any points or ask questions in general?
Yeah, let's keep it flexible.
Okay, awesome. So actually, let's go back to Kevin's question, which was there. So this is for Divya. There was a follow-up question by Kevin. Can you talk about how much effort / money / time is required to create your data set? What part was challenging, just as a reference? Divya, are you there?
Hello.
Yeah, Divya.
Hello.
Yeah, we can hear you.
The question was like, can you talk about how much effort, money, and time is required to create your data set. So actually, this data set was developed. It takes actually a time of approximately 3 months for us to come up with data set, which is in which most of its part has been post edited. So we have in our lab three professional annotators and two translators who did this job. So about cost, I cannot say because that is something we students don't deal with. It's departmental thing. So we have this professional group that does such kind of things. And what part was challenging? So for us, the most challenging part was to come up with a common set of annotation that we find were the most challenging thing. Does that answer the question? Hello?
Yeah. Yeah. So I guess I'm wondering, this 3 months does seem like quite a lot of effort. So maybe we can't expect to say what you want to double the data or want to do it for a new language. It does require some effort then.
Sorry, your voice is not that audible to me.
Oh,
Can you
okay.
repeat?
Yeah, so I was just commenting that from what you said, 3 month effort, that does seem like quite substantial.
Yeah, it was actually a work of 3 months. So over the period of time that the data set development was a continuous process. So we were crawling the data and were getting it translated with the Google API, and then it was post edited, and then again it was verified by one more translator. So it took us approximately 3 months for this to develop this data set.
I see. Thanks.
So actually, I have a follow-up question on that. Can you comment on how much of post-editing effort was required? Because I'm sure that the Google API translations were not at your requirements. So how much of the overall annotation or cleaning time was spent on post-editing?
So actually, we have a separate group for that who does this part. For me, it was like they were involved continuously in this process, and as we make them data available, they do this. So right now, I can just give you this brief of 3 month period was required, but approximately how much of effort they have put in, that is something that I cannot answer from my part.
Okay.
Sorry.
Okay, that's okay. Yeah, again, with regards to the data set, when you do annotation, like if one of the linguists or translators performed one kind of annotation and the other linguist or annotator has another annotation, have there been cases where there is like discrepancy between them, or did you have any kind of agreement calculation where all annotators or two annotators agreed on a particular annotation? Can you comment on that?
Yes, we have actually, we basically have 3 annotators. So we take majority whenever we actually come up with, if 2 of them voted for a similar thing, then we took that as a common annotation. Hello?
Okay. That makes sense. Okay, we still have 15 minutes, so please keep the questions coming. We have sufficient time.
Hello. I've been in several sessions this morning. I'm trying to keep track of which one was this is for. The one about tags, markup tags in the source text. Was that in this track or another track?
Markup tags in source text. I don't see anything.
I think I'll jump out into the other question answer, see if it's there. Oh, thank you. I'm getting the answer, another track. Thank you.
Okay.
See you later.
So I have a question. Maybe this is a joint question for both Maya and Divya. So Maya, you've done polarity annotations as well, right? In your analysis. If so, I'm curious if you have any comments on how that might relate to Divya's work on sentiment classification of MT outputs. Like from what you're seeing in polarity, what kinds of problems are there? Or negation, I guess you said negation. Yes.
Yeah, so that's interesting. So, I mean, we didn't do anything in that direction, but when I was preparing the data, I wanted to have actually a balanced set with positive and negative reviews. Also, just in case that some future work maybe wants to check polarization and whether it's preserved in the translation and stuff like that. So the data is publicly available. So, I mean, I might come back to this one day, but if anybody else wants, it's welcome, yeah. But there are also IDs and then the score, so it's clear which is positive, which is negative. So
I see. That's cool.
yeah.
Yeah, so maybe someone else will take it up.
Maya, I have one question for you as well. So one of the errors you identified was noun phrase errors.
Yes.
Yeah. So do you think like there might be other phrasal errors like verb phrases or other linguistic phrases? And do you think if we use some linguistic annotations as features in these models, then do you think these errors can be mitigated?
Oh, that's interesting question. So the only really linguistic phrase I noticed is this noun phrase. I mean, it can even be also classified in rephrasing, because in target languages, the problem is that you have to rephrase. You cannot just put nouns and adjectives, and you have to know how to put it. But still, I noticed that it's really typical, like separate class. And then even in German, although much less, in German it's compound, which is that usually also you just put all those guys together, but not always. So, but yeah, so for the other things that I notice is also like multi-word expressions and idiomatic expressions, which are also going wrong. So this is also kind of subclass. So this rephrasing class, it could be maybe analyzed more to see, for example, how many multi-word expressions are there and which kind of them.
Yeah. I mean, given that this class is the biggest one, the most impactful one according to your paper, maybe some fine-grained analysis makes sense.
Yes. And also what I also noticed is sometimes, I mean, some systems tend to more like it fails to and produce some kind of literal translation, which is not even literal translation, it's just bad translation, but it follows source. But sometimes it rephrases, but in a wrong way. And then I didn't do any real quantitative analysis. I just noticed that it's also a little bit system dependent. So some systems tend to do more one thing and some systems the other thing. So maybe it will be also interesting thing to check.
And is there any way you can connect these translations to the data that was used to train these models?
You mean to training data?
So the training data may have some biases or some errors or some distribution. So is there any way you can connect them?
Yeah, so there are two in-house systems. So I mean, I can look into this training data and see whether there is something there. But for the three online systems, I don't know, because we use, as I said, two our systems and three like Google, Amazon, and Microsoft. So I don't know what's there.
Okay. Thank you. So Kevin has a question for Tamali, or just general discussion with all participants. Where do you think unsupervised MT should go next? What are your promising research directions in your opinion? So people can feel free to jump in. Tamali, are you there? Oh, seems like Tamali has left.
Yeah, maybe she got disconnected.
Maybe. Yeah, but that's a good question. Unsupervised MT. Are we talking about like an unsupervised MT without using any parallel corpus at all? Or are we talking about unsupervised pre-training and then doing fine tuning with very small amounts of corpora?
Yeah, maybe both is fine. It just seems like there's a lot of work in both of these areas.
Yeah.
At this conference as well, there's a few papers.
So actually, Tamali has both the papers are actually by Tamali, I think. So she's an expert, but she's left us.
Yeah.
I think
So
for me,
Eileen-
it's, oh, sorry.
Go
Yeah,
ahead.
please go ahead. Please go ahead. Please go ahead.
Yeah, I think for me, it's on out of domain data, or like using, like you have one domain in one language, one domain on the other. Kevin and I actually have a paper that addressed this from a year or so ago. Yeah, because it seems like unsupervised MT works well between two languages which are like relatively high resource and which the domains match relatively well. But once the domains don't match, it's very bad. So that would be my next venture, is the domain mismatch problem.
Yeah, I also wonder if it's already in use in industry, or is still very much a research endeavor. I mean, even for low resource cases, right? If I want to deploy for a low resource language and I don't have anything, I wonder if people actually use these techniques yet.
Maybe the pure unsupervised approach might be a bit too difficult. I think it makes it's easier to get monolingual data, do some denoising pre-training, and then do fine tuning on small amounts of corpora. I think that's a more feasible approach, because the UNMT approach itself is quite data hungry, as we have seen. It definitely needs an order of millions of sentences for, even to get it work. And then on top of that, some cross-lingual embeddings are required for initialization for distant languages. Otherwise, it just doesn't work.
Yeah, I agree.
We have 6 more minutes, but I think the participants are beginning to dwindle each minute that passes. So yeah, the session is still going to be open for the next 6 minutes. So if anybody has anything they want to discuss, anything they want to point out, or maybe someone doesn't like the way machine translation is proceeding, if you want to complain about it, please just raise any issue. We are more than happy to have a discussion on that.
We can also end a little bit early so that people
rest
before
Atsushi
the
has a
next
question.
session. Okay.
Atsushi has a question. So given the success of pre-training models, what should be the right baseline for low resource or zero resource scenarios? That's a good question. What should be the right baseline for low resource or zero resource scenarios? That's a good question.
So are you asking because pre-training models are using other data sets? Is that the concern?
Yeah, for instance, MBOT really works as a pre-trained model, and you can fine tune it, or just use the synthetic data based on the pre-trained models to start to initialize a good model. So I wonder whether the pure low resource or pure zero resource scenarios are still realistic or not.
Yeah, You mean like
I mean,
yeah, go ahead.
I feel like for some languages, the very low resource is still valid because all these pre-trained models, even the massively multilingual ones, obviously do not contain every language. In fact, my guess is they might be missing like large groups of related languages, low resource languages that were not present in high enough amounts of data to be used in the massively multilingual pre-trained model. So I feel like a fair baseline is if there's a supervised model that's easily available and works well for that pair, then that should be the baseline. But for some languages, that's not going to be true. So I think it's probably going to be language specific what would be fair. Because like if you're saying, oh, I got, and I'm guilty of this myself because I work on unsupervised MT. But if I'm saying, I got a blue score of 25 with French English, when are you ever going to need to do that in a fully unsupervised way? So I feel like I should personally probably compare to the best supervised model that I can get because that is realistic and that's what's for very low resource languages, even those good supervised models aren't going to exist. I don't know if people disagree with me on that.
So actually, then the question is, should we really be working on French English translation in an unsupervised setting, or should we actually be working with languages that need unsupervised, where actually there is no parallel corpus or very little parallel corpus?
I think you can learn things though from the high resource languages in the unsupervised setting. Again, mentioning that paper, it was from WMT 2020 that Kevin and I worked on called When Does Unsupervised Machine Translation Work? Even using higher resources languages like English, French, and Russian English, we saw this domain mismatch problem. So I think you can certainly learn things from high resource languages in an unsupervised scenario. But if you were to make a real translation system, you wouldn't do that for French English.
Right. So I guess we need to probably work on these endangered languages, and maybe those would be a lot more realistic to work on.
Yeah, I think the struggle that I have is like from a development perspective, is it just going to be way too hard to start with those things? Like, should we start with the higher resource ones, or are we like hiding some issues that are going to arise in the true low resource settings by using downsampled high resource data? And I think we probably are losing a bit of the challenges that come in true low resource languages.
I agree with you.
Yeah.
Does Derry want to say something?
Yeah, I think one of the challenge I find working on the truly low resource languages are the lack of data, actually, like to get a benchmark data set to test and to evaluate our models on. It's hard to find, especially if you look at like the zero level language, there's not even monolingual text on them. So yeah, it's kind of hard in that sense, but I think we need more actually benchmark data sets on these languages so we can actually develop models for them. Yeah.
That's what LREC is for. So I think we just have no
Right.
choice but to make such data.
Yeah, I think it's really necessary because I think, like you mentioned, there are challenges to like truly low resource languages that we cannot simply simulate with downsampling high resource language.
Right.
Like there are language similarities and then script difference, vocabulary difference, and all those stuff. Also, that makes me wonder whether the baseline for like low resource machine translation should be something that is like specifically engineered for that particular language, or should we develop something more general purpose, low resource MT?
I think that's an open question.
Yeah.
Yeah. So anyways, it's time to end this session because the keynote has already started actually. So I want to thank everyone for attending this session, and let's thank all of the authors and the people who asked the questions. Thank you so much. Is it okay to end the session, Kevin? Okay, cool.